Hi everyone, welcome to AI Exact channel. This is Akash Gangwar and today we'll be studying differentiability lecture 2. So this lecture is going to be a little bit theoretical and we'll be studying about algebra of differentiability and the entire lecture is going to revolve around that only. So let's start with an example from the previous lecture. So this is the example. So the example says that the set of all points with the function fx equals to x upon 1 plus mod x is differentiable is. So for solving these questions, the basic thumb rule is to first check the continuity or discontinuity of the function. Now we know that this is a rational function fx equals to x upon 1 plus mod x. Sorry, mod x. Now for any rational function, it is always continuous unless we have a point where denominator becomes 0. But we can clearly see that this is a modulus function over here. So the denominator is always positive. So we can clearly say that this function is always continuous. So we are not getting any indifferentiability point with the any discontinuity point with the help of any discontinuity point, right? Now the critical point over here is 0. So let's try to open up the definition of function. So that would be x upon 1 plus x. We are opening x mod x is positive when x is greater than equals to 0. And in case of x less than 0, that would be x upon 1 minus x, right? Now we can clearly say that 0 is the point where definition of function is changing. So we have to check at the point 0. At all the other points, the function is continuous and smooth, so that's why it's differentiable. So the only point of worry is the critical point, that is 0. So f dash 0 plus, that would be limit h approaches 0, f of 0 plus h, that would be 0 plus h upon 1 plus mod of 0 plus h minus f of 0, so that would be 0 divided by h. So that comes out to be h upon, since h is positive, we can open it directly, 1 plus h times h. So that would nothing be 1 upon 1 plus h. That comes out to be 1, right? Similarly, f dash 0 minus, that would be limit of h approaches 0, f of 0 minus h, that would be 0 minus h upon 1 plus mod of 0 minus h minus f of 0, that is 0 divided by minus h, right? So in that case, we'll get minus h upon minus h times 1 plus h. So again, that comes out to be 1. Now we can clearly say that the function is differentiable everywhere because the critical point was 0. It's differentiable over here as well because LHD equals to 1 equals to RHD. So A is the correct option. It's differentiable everywhere, right? Now let's talk about algebra of differentiability, and it's nothing but a continuation or a recap of what we studied in limits and differentiable and continuity. So basically the table is going to be same, but examples are going to be a little different. So what we did over there was, let's say we have function fx and gx. So in that case, limit was existing or it was continuous. This was continuous or limit was existing. We tried to add them, subtract them, divide them, multiply them, and we saw the results. What kind of results we are getting? Both the cases, discontinuous plus continuous, discontinuous multiplied by continuous, and all sorts of cases. So we'll be doing the same over here as well. So we have function fx, we have function gx, we have f plus minus g, and we have multiply f multiply divide by g. So this is our table. Now let's say f is differentiable, g is also differentiable. So obviously f plus g would be differentiable and f multiply or divide by g is differentiable unless we have a denominator part which is 0. So that is obvious, that is very obvious, that is very intuitive. So that denominator part shouldn't be 0. In all the cases, uh, if f is differentiable, if g is differentiable, f plus minus f multiply divide, that would be differentiable. So that is very intuitive. I won't be taking any examples. You can just try out with some example and you can derive it, right? Now the important part is, let's say f is differentiable and gx is non-differentiable. Now the important part is, let's say we have fx as differentiable, gx as non-differentiable. So in that case, f plus or minus g, that would again be non-differentiable. But f multiply f divided by g, that can be differentiable. So maybe or may not be differentiable, right? Similarly, let's say we have this as non-differentiable, this also non-differentiable. So again, this can be maybe, same with this one. So we'll take the examples for these ones, the critical ones. So the first example is derivable plus non-derivable. So let's take the example of x and mod x. We know that mod x is non-differentiable at x equals to 0, but x is differentiable at x equals to 0. So let's try to form a function fx that would give us x plus x for x greater than equals to 0, because mod will open as positive, and in that case x less than 0 will be getting 0 over here because that would open as negative. So this is nothing but this is 2x. So what we are getting over here, we are getting 2x graph is like this, and x equals to 0 is the fx equals to 0 graph is like this. So we are getting a sharp corner over here, and when we get a sharp corner, that means the function is non-differentiable, right? So we can clearly see that differentiable plus non-differentiable is always non-differentiable, or we can do the -1, differentiable minus differentiable is always the non-differentiable. Now let's take the other example, differentiable multiplied by non-differentiable. So again, we'll take the same examples, x and mod x. So this is non-differentiable, this is differentiable. Again, let's take the point 0. Let's define the function. So that would give me x square when x is greater than equals to 0, and for x less than 0, we'll get minus x square. Now let's look at it graphically first. X square would look like this and minus x square would look like this. So we can clearly see that there is no sharp edges over here. It's actually very smooth. So with the help of graph, you can say that it's differentiable. But let's look at it algebraically. So we'll get f dash 0 plus, that would be f of 0 plus h. F of 0 plus h would be for this function. So that would be 0 plus h whole square, limit h approaches 0 minus 0 divided by h. So that is nothing but h, and that is eventually 0, right? Now f dash 0 minus, that would be limit h approaches 0, 0 minus h whole square minus 0 divided by minus h. That again comes out to be, sorry, this is minus over here because we are using this function. That again comes out to be h, and that is nothing but 0. So we can clearly see that derivable function into non-differentiable function. So basically differentiable multiplied by non-differentiable, it can be derivable as well, because here we are getting LHT equals to 0 equals to RST. Now let's look at the third example, that is non-differentiable plus non-differentiable. It can be plus or minus over here, right? So let's take one example, mod x minus mod of sin x. Now both these functions are actually non-differentiable at x equals to 0. So mod x would look like this one, and mod of sin x would look like this one at x equals to 0. So both these functions are actually non-differentiable at x equals to 0. So considering the sin x function over here, so we are considering the domain of, let's say, minus pi by 2 to pi by 2 to avoid confusion, right? Now let's define this function entirely. So let's say this is our fx. So let's break it down. So what we'll get over here, for x greater than equals to 0, we'll be getting x minus sin x because x is positive, and sin x and both x will open as positive. For x less than 0, we'll be getting minus of x minus sin x, right? Now let's try to differentiate it. What we'll get over here, we'll get 1 minus cos x for x greater than equals to 0. We'll get minus of 1 minus cos x for x less than 0. Now we have to just find LST and RST. For RSD, right hand derivative, we'll be using this function. Again, that would come out to be 0. So basically RHD is nothing but 0, and also LHD is also 0. So we can clearly see that over here, that this function was non-differentiable, this function was non-differentiable, but the outcome, the summation or the subtraction, came out to be differentiable. Now let's take the example of non-differentiable into non-differentiable. We'll take the same example once again, mod x and let's say sin x, mod sin x. So let's try to define the function. Fx would be, for x greater than equals to 0, we'll be getting x dot sin x only, right? And for x less than 0, we'll be getting minus x dot minus sin x. So that is nothing but x sin x only, right? Because both are opening with negative. Again, we are considering the domain of minus pi by 2 to pi by 2, right? We are considering this domain. So for this part, for the negative part, both of these are opening from negative sign, so it eventually becomes positive. And for positive, it's already positive. So function actually becomes x dot sin x, right? So this becomes a function. So this is nothing but this only. Now what is this This is differentiable. This is also differentiable. What we'll get? A differentiable function, because in the first column we saw that, in the first row actually we saw that when a function is differentiable, both the functions are actually differentiable. Multiplication, summation, division, subtraction, everything is differentiable, right? So that's how a non-differentiable function multiplied by a non-differentiable function can be right, not always, can be differentiable as well. Now let's move forward with these standard derivatives. So we have seen few examples, few derivations actually. We saw the derivation of cos x, we saw the derivation of 1 by x. So you can derive all these questions, we can derive all these standard derivatives with the help of first principle. So you don't have to really do that. You can do that for the understanding purpose, but eventually you have to remember these functions, these standard derivatives. So for sin x, we have cos x. For cos x, we have minus sin x. For tan x, we have sec square x. For cot x, we have minus cos x square x. For sec x, we have sec x tan x. And for cosec x, we have minus cosec x cot x. Those are very similar in nature, right? For log x or ln x, we have 1 by x. And for log of fx, we have 1 by fx dot f dash x. Basically, the chain rule, nothing but chain rule. And for x raised power n, we are having n times x power n minus 1. So that's why we saw that when we are doing for x raised power minus 1, what we are getting over here, minus times x power minus 1 minus 1. So that would be minus x square. That comes out to be 1 by x square, minus 1 by x square. So the basic point is you have to remember these derivatives, right? Standard derivatives. Now let's continue with the algebra of differentiability. Let's say we have a function over here, hx equals to fx plus gx plus, let's say, kx, right? Now we have to find d by dx of hx. What that would be, d by dx of fx plus d by dx of gx plus d by dx of kx. So basically what we did over here is we just distributed the d by dx in the entire function. So that is how it works. Let's say we have a function, let's say we have a function x square plus 2x. So when we are differentiating it, so we'll be doing d by dx of x square plus d by dx of 2x. We will be doing individually and adding it, right? So that's how it goes. So now talking about the next property. So let's say we have a function hx equals to k times fx. Now, if you want to find d by dx of hx, so that would be d by dx of k times fx. That would be k times d by dx of fx. So basically the constant function, constant number, constant function comes out. So this is also very intuitive. So what you can do, you can just use the first principle to derive it. Otherwise, you can just remember it, or it's very intuitive to bring out the constant outside. Now the third property is product rule. What does this say is, let's say we have function fx dot gx, hx equals to fx dot gx, and we want to find derivative of dy dx of fx. So what we'll be doing over here, we'll be doing f dash x dot gx plus g dash x dot fx. So this is the product rule. So if we have to differentiate a function which is in the product form, we'll be doing this one. So let's say we have a function x dot sin x. So we have hx equals to this function. So what we'll be doing over here, we have to find dy dx of hx. So what we'll be doing over here, this is fx, this is gx. So f dash would be 1 times sin x, that is gx, plus g dash, that would be cos x dot x. So the derivative would come out to be sin x plus x cos x. So this is how you have to apply product rule. Now the fourth property is quotient rule. So let's say we have a function hx equals to fx divided by gx. Now we have to find d by dx of hx. That would be f dash x dot gx minus g dash x dot fx divided by g square x. Now at times during the examination, you might forget that if f dash x was coming first or g dash x was coming first. So to remember this, you can just follow this one trick. So we know that let's say we have function fx equals to, not fx, we have function hx, that is 1 by x. So here 1 is fx and x is gx over here. So we know that h dash x equals to minus 1 by x square with the help of x is power minus 1, derivative of x is power minus 1, right? So now you can use quotient rule over here. So for f over here, f is 1 over here, g is x over here. So now let's try to apply this one. Now derivative of 1 would be 0 multiplied by x minus g dash x. G dash is over here is 1. 1 multiplied by 1 only. Divide by x square. So that comes out to be minus 1 by x square. So you can verify it with the help of this one. So if it comes out to be positive, then probably you're doing it wrong. Now the last rule is chain rule. So let's say we have a function hx equals to a composite function f of gx. Now we have to find h dash x. So what that would be f dash gx dot g dash x. Let's say we have a function hx equals to f of g of x, sorry, f of g of, let's say, kx. Now h dash x would be f dash dot g dash dot k dash. So it keeps on going. So let's take few examples to understand this one. So let's say we have a function hx equals to sine of x square plus 2, right? So if I try to write this in the composite form, so what we'll be doing, we have fx equals to sine x and we have gx equals to x square plus 2. So we have written this one is nothing but f of gx, right? Now we have to find h dash x. So for that, what we'll be doing, we'll be first differentiating sine. So that would give us cos of square plus 2. Then we'll be entering inside the composite function. That would give us 2x, right? Differentiation of x square plus 2 is 2x. So let's make it a little more complicated. Let's say we have a function hx equals to sine of cos of x square plus 2x. Let's say this is the function. Now we have to find h dash x. That would be cos of cos x square plus 2x dot multiplied by basically differentiation of cos. That would be minus sine x square plus 2x multiplied by differentiation of x square plus 2x. So that would be 2x plus 2. So this is how chain rule operates, right? So you can practice more examples with the help of notes and examples which I'm going to upload in the portal, but this is how it's going to be. So today's lecture was still here only, and I'm sure this one was actually a little heavier on the theoretical side. So what you can do, you can just log into the portal and you can practice more stuff from there, and that is the only way to get your hands clear on these ones. So let's meet tomorrow for the next lecture, and thanks for watching.